Hey, you want to fire this up?
I remember my analysis course, the professor spent like a surprising amount of time trying to tell us exactly how a USB connection worked. Maybe that's a bit too in depth. I certainly don't really remember how. I mean, it is interesting to live only like one bit at a time, but
Yes.
so it would be under 6194. Presentation. Is this computer owned by the school? It's got like the school background.
Technically, yes. I mean, I'm the only one that uses it.
Yeah. So I've never seen that like desktop background outside of computers used by the university.
Poster presentation.
Yeah, I'll let you change that real quick. Do like class presentation. Sure. I'm used to calling my title of PowerPoint presentation is the fun. All right. Without thinking about it. She found it in her desk. What? No, this is my personal one. But I guess we don't have enough spots on this machine to. What? Oh well. I read that using a green laser pointer to play with a cat is quasi animal abuse because the green light's so much more intense it destroys their eyes. Not that shining a red laser is optimal, but it won't be an immediate risk for permanent eye damage. Hey. That was weird. It occurs to me being up here that this is actually a really awkward angle.
Yeah.
I never really noticed it. Yeah. I guess I just.
Always talking to us too.
Speak on this. All right. Hey guys, my name is Nate Wood. You may or may not know me, probably not. But today I am here to talk to you about convection in arc weld pools. So this is the title of the paper, citation information, introduction. The purpose of this paper is to present electromagnetically and convectively driven heat flow, the model for this heat flow within the melt pool of like an arc weld. And this is different from the models that we talked about for impacted convection to some degree. This paper also factors in all of like the electromagnetic going on in the arc weld. If you might remember, an arc weld is an electrical process that's a very high amount of current through the welding metal, and that current passes into the weld beam. And because now everything is, the welding is electrically conductive, that generates a whole lot of electromagnetic force. And then we like to produce a lot of dynamic other types of data which we talk about, not necessarily included. To my knowledge, this is one of the first, if not the first, paper to do this. It's a rather old paper. This is from 1983. So it was a pioneering work in the subject. So the model which they describe makes 5 key assumptions. The first assumption they make is that we have laminar flow within the melt pool. So within this melt pool here, we have laminar flow. The geometry, they call the geometry of the melt pool stationary. I can't actually figure out if they imply that the electrode is moving in like a moving coordinate system. If you're talking about a steady state, what literally is the electrode being held at a fixed point over the mill. The length is complicated, but it is at steady state. And it's steady state with assumed melt pool geometry according to this relationship, where we have a specified melt pool depth, specified melt pool width, and then extrapolate, C as a function of R. Right? They're neglecting radiant heat losses, which is somewhat reasonable for most materials, given that the Stefan Boltzmann constant is our negative form. So unless you have some really outrageous gradients, like material, and they also neglect momentum transfer due to the arc, which I assume means some like factor where the arc is like causing splatter or some other factors to come out of the melt pool or some other kind of weird momentum transfer. I'm not an expert in this area, like they're also assuming cylindrical symmetry about the material. So their model is rather complicated. So the governing equations start off with continuity, otherwise known as conservation of mass. You may see this from your fluid mechanics courses. And then additionally, we have our conservation of momentum, which is, to my knowledge, this is like a modified version of Navier-Stokes. They modify it to include this body force. This body force includes not only buoyancy, but also electromagnetism. And what they're not doing in this paper is that they're solving all these very complex heat transfer and fluid flow effects, which they're enumerating explicitly in the paper, but they're also doing it in all natural things. They're not even allowed to. They're also doing that in the background, all the currents. So right off the bat, this is already an extraordinarily complex multi-physics nonlinear model, and we haven't even gotten to the heat transfer yet, which is specified. So we have our temperature coupling into our momentum, coupling into our mass conservation, coupling into our electromagnetism. Models of this order of complexity are one of the reasons why when Professor Helsing throws like these simulations up, they say it takes 100,000 CPU hours to run a single well track. Models of this complexity are why. Because you need this kind of like extreme multi-physics to adequately capture the processes. No model is complete without boundary conditions, so of course I'm going to list them here now. So first off, we assume symmetry about the z direction and about the theta direction that can be a cylindrical coordinate system. We assume conditions of zero slip on the interface between the melt pool and the surrounding solid metal, and we also assume that this interface here has temperature uniformly equivalent to the temperature, which is less important continuity reveals liquid to solid. They specify the nature of the current and heat fluxes like impinging upon the top surface of this melt pool as a function of radius. So this represents flux coming in from the electric arc. This represents current coming in from the electric arc. These are independent models of boundary conditions and how much energy is the arc of the core and uses. And their exponential is next, we also assume that there's this Marangon convection at the top surface of the melt pool, which was a pioneering innovation in modeling physics done by this paper. And I believe anyone who has done this before, and one of the major conclusions of the paper, is the influence which this Marangon convection has on the dynamics of the pool. They enforce one last constraint. It's kind of awkward phrase. Basically say there is a third kind of loss in the evaporation, right? And they're not completely lost due to evaporation. A function of they say this small has to be always less than being projected by the. So it's like indirect constraint on the max level of in terms of like amount of paper they are. Their solution strategy is to approximate these equations with finite differences on an 8x10 grid, assuming symmetry. And honestly, discretizing this set of equations, they don't spend any work on that. Yeah, I'm not going to talk about how finite differences works, but it's like a numerical approximation scheme. So the simulation results, they throw into this giant. And I'm not going to spend a lot of time on this, but they want you to take a look at the maximum velocity level. We run simulate all of these processes. And they take the maximum liquid velocity. We want you to know, first off, how much faster the convection level becomes as you increase the environment. We also want you to notice how much faster you can start making the our more focus on this right table, but that's how they present the results. So that's how I'm presenting it here. They do have graphs, and these are actually really cool graphs. So what's happening here on the left column, isotherms, happening on the right column are velocity. So what I want you to notice here, this represents more sharply broadly focused beats, less speed. More sharply focused, we get helpful. It should make it good as best that if you pack the speed into a smaller amount of area, obviously intuitive. But we also see there's a very strong degree of iron bounding convection at the top surface. Again, it made sense to us in 2018, having studied this for quite some time, and at 1983, this was a very new and innovative thing. Right? Something that they also demonstrate here is the presence of total convection. Will happen here, and effective will happen here opposite. And what they say here, they say the paper is flow, which here is due to Paragoni effect, this effect will flow down here is due to electromagnetism. They demonstrate what happens when take Paragoni protection as a boundary condition, and you actually drop this over the effect highly get zero electromagnetism. So, but in the paper they know that these are less produced, far less realistic isotherms, and also it slows down the total speed of convection and melting to unrealistic use. Makes sense? To conclude, they say in the paper they found some citations that the accurate mark affects surface velocity of the stating is representative of the physics of the novel are consistent with the Horn values. They also show using this figure from another citation that factory mark values can actually impact. Personally, I think that I feel like it. I feel like the industry decided to make what is interesting here is that the fact that these two convective loops are going in opposite directions means there's a stagnation point here where they meet, right? And what they say is that this is an explanation for a known effect where in certain wells you get like a region of unmixed material right here. So like the point of the well is to smoothly join two metals together to form an alloy, right? Perfectly joined alloy. This always happens. So I want to see a region where you get like occlusion or unmixed materials like working in the middle of the well. And they are saying this is due to the stagnation point in the well pool convection. Because there's stagnation, there's no like metal flow like happening. And so the two adjoining pieces of material can't actually flow into each other and merge. Does that make sense? Additionally, they take that entire complex, they reduce the total extent of vaporization. The paper wraps up by justifying all the assumptions they made in the opening paragraph of the construction. They say the assumptions is reasonable given that they took experimentally derived values for all of their well. They say they do like a token Reynolds number analysis and say that based on this, the assumption of laminar flow is justified for a small well. Next, they again cite all these experimentally derived well values and experimentally derived weld pool shapes to justify their assumption of known weld pool geometry, at least in San Diego. And finally, they cite some experiments that justify their assumptions of the nature of the heat flux and current distribution. They do acknowledge two important limitations. They say that for one, large weld pools may display turbulent flow, and then this model just totally collapses. And two, their assumption sharply constricted the total amount of information in the weld pool. And they say that for weld pools displaying a large degree of vaporization, it appears that the heat flow into the material because actually it's going to have work well and the problem dissipated or all sorts of other weird effects that they can't precisely quantify. The ultimate conclusions is that these models validate or at least provide an explanation for experimental work, which demonstrate the dominance of Marangoni effects in this weld pool convection. And they also provide an explanation for why we sometimes see unmixed effects. They supply an application, the obvious application is predicting weld pool geometries, characteristics of weld pools for known inputs. And then they also say they want to expand their work to include non-stationary, like non-steady state, transient weld pools, varying process everything. I don't know how well that worked out for them. Strengths of this paper. It has a very clear, very concise presentation of the model and the physical interpretation. I really also all of their especially where they weaknesses. I don't like that people say, but I really don't. I think it's super wrong. Especially since I'm continually referencing it throughout the paper. I would have put a lot of these colors in the graph. One more flat. And then I would have spent a bit more time. I don't know what I would do with the space constraint. I don't think this is a constraint paper, but I would have spent a bit more time on the discretization with funny difference, because that can be a whole thing on its own. Especially since there's a sentence in the paper saying we use quote unquote non-uniform grid spacing, which is a famously thorny question in mind because of how hard it is all of your discretization, especially for like the non-rectangular grid, they were not have this weird meltdown shape. Especially, and also, yeah, just concerns of, repeated replication. How you going to replicate the study? If you don't know how they actually built it, you get an entirely different time to do for a different set of assumptions. But yeah, questions? That's all I had.
So, like, what are the possible solutions of
That coefficient is one of the this coefficient, you mean? Positive, they said you can get a positive number if you have certain amounts of inclusions or other non-uniform elements. You could,
shear stress on the top, driving really starts to happen with the lasers. This will be the case for now. So this is going to change the
Yeah, we have one of right. If this is a positive, we have conquest. It's so weird because it's not supposed to do that, but you have a certain like theories, you know.
the Deborah Giger talks about the vast majority of the metal is going out. So that creates you see the clock bodies. That does is it actually causes the non-pool to widen and break. In the opposite direction, hot fluid, it's hot as essentially at 0.00, right? And it's driving it down. So it's the material.
So you mentioned the opposite, which is the flow of stagnation and right? But also you have to investigate well, where is that stagnation point? Oh, no. Right here. Well, because you have one region of flow that's doing this, right? We have another region of flow that's doing this, right? And so there's a stagnation point right here. And what's happening with the stagnation point is like, say this is our metal A, and this is our metal B. The point of a well is to make the AB alloy everywhere in the well. That's obviously not going to happen if no material is flowing. Like, you're going to reach up like yeah. So this big process could be well, what they say is that the RNA dominate, but the electromagnetism is still toward specific, precisely situations like this. Okay. Like it is important. It is not the RNA effects are, I guess, dominating and a lot of properties. Well, because it produces the highest velocity right here, which is where like a lot of this gradients. But at the same time, this is also important. For another reason, it feeds the nature of convection out here to continuity. So you can't, like, just because one aspect of the physics dominates the other, that doesn't necessarily mean you can neglect it. And this, I guess the whole point of this is showing this specifically why.
It's tough to get.
No, I think the numbers they were explicitly given were all things like surface velocity. This is, I guess, the closest you would get is a comparison to surface velocity crossed by about a factor of 5, so maybe you could say it's like a factor of 5 to 10 or something. Dominance.
It's a another question. I always kind of amazed that they have
Yeah, I doubt that.
those zeros are born.
Like, they must have
I
been.
never visualized like that.
That's actually another thing that I like to talk about. Is that another thing they were talking about this is they call it finite difference. This was before a lot of commercial finite difference by Elvin Coates. They had They had to do this manually, 100% manually. They didn't report a bit of it. I would. But yeah, I doubt that happened. They were running, their message was like the world's biggest company cluster at the time. I said they said they did go to the national lab to do this, but maybe one of them will start with.
Still impressive.
Because this is not a trivial field.
Any questions? Thank you.
You want me to put this presentation on like your desktop or something?
So we left off on Tuesdays, in this lecture, uh, going through just some like the major overview of material extrusion processes. And now we're going to start to get into what's actually happening. So starting off with this is their goal. Build process, material extrusion processes. Heat transfer. But for the processes are not processes. So is I asked on Tuesday, I think pretty much everyone has seen MakerBot or equivalent new definition file full running before. So I think if you just watched one, it wasn't exactly sure what's going on. Just look at what's actually in the guts of this. You know, build stage, either variety of different systems, some of which the stage does all the moving and the nozzle just stays constant and constant location, or ones in which there's every way you can think to do it. Some of them, the nozzle does all the moving, the stage stays in a constant expedition. Some they have the nozzle moves X, Y, stage moves in Z, a bunch of different variations there. And then when you have these liquidifiers or liquefier regions, what's going on is we have build material, which we talked about very briefly on Tuesdays. This is a wire or filament of the polymer you're trying to build with. And for most of these systems, they have these pinch rollers, and these rollers just grip onto the side of this filament, and then they drive it into this liquefier. The liquefier is basically just a resistive heat source. And these are oftentimes temperature controlled. So this would be has feedback loops, that keeps a certain temperature in this. So over the course of going from the filament, which is a solid material, and the liquefier goes to, I'm putting quotes in here saying liquid, and I'll talk about what that means in a second. And then once it leaves, then the nozzle, it becomes solid again. And the solid transition is a little bit fuzzy, so I wanted to talk a little bit about that. And we have someone in chemical engineering. Don't correct me if I'm saying anything correctly about polymer science. I'm definitely not a polymer scientist. But this is actually fundamentally different than what we talk about when we talk about melting of metals. Melting of polymers are very, very different. That's good here. Okay, so when we say a polymer melts, we actually do not mean melting. All right. So if we look at what a polymer is, it is oftentimes called as a amorphous material. So this means that the majority of the polymer, this is below what we call the glass transition, well, not we, what people call the glass transition temperature. It's composed of these chains, which are connected by what are called secondary bonds. These are weaker bonds, not covalent bonds, such as the weaker bonds, such as van der Waals bonds, ionic bonds, other types of bonding. But these are fairly weak bonds that are holding this polymer structure together. Some polymers can be highly crystalline, so they'll have really large concentrations of crystalline regions, which are held together by covalent bonds. So this region here would be the crystalline region where you have some sort of organized structure in the polymer, but especially the materials that we're talking about for additive manufacturing, usually very low crystalline content. Mostly looks like this. Here, this is one. So we talked about a material polymer going from an area where it flows, sorry, doesn't flow, to not flow. What we're really talking about is changes in this amorphous region, not actually breaking crystalline region, which would be now would be melting. So what we're doing is we're not melting the material, we're raising the temperature above this glass transition temperature. That's basically breaking down these secondary bonds here. This is also a reversible process. So it will continually, if you thermally cycle this, it'll go from getting above the glass transition temperature to below it. I guess you do a lot of polymer processing as well. So please speak up if you think I'm representing something correctly. So this is a really simplified version of what glass transition temperature looks like. This is specific volume. This is a measure of density, right? And so if you have some sort of material and you basically heat it, you get then this expansion of the material, which then goes in kind of a linear fashion. Crystalline polymers, which are not used as much in additive manufacturing, has a very, very sharp transition in this. So you hit this melting temperature, and it has a very, very fast compaction as you reform those crystalline structures in the material. So what we're really talking about is going to, or say, when we say melting in polymer melt processes, we're not actually talking about melting. We're actually talking about going to either side of this glass transition temperature polymer material. Some other things that are kind of just general overviews of what's going on here. This is just a generic polymeric material, looking at the viscosity of that polymer. Viscosity. And this is that you get a change in the viscosity of the material around this glass transition. That's where you get the abrupt change. So what we're talking about is not this really sharp interface we see in metals where you go from solid to liquid, but actually this kind of fuzzy zone in the middle where you are actually fairly slowly changing the viscosity on each side of this glass transition. That's the idea. So it's not melting, even though I think everyone who looks at a MakerBot system and says, oh, it's melting plastic, right? But it's not technically melting. It's raising above this glass transition. Okay. So just kind of belabor the point here. Sorry, I kind of covered this up. This is TG. This is TF. Okay, it's also important to note that not all polymers have a melting temperature. Okay, so if there is essentially zero crystalline component of that polymer, you can't get it to melt. You can definitely get it to go above some sort of gas transition temperature. But these are some. This is just coming from a textbook of different polymers, looking at glass transition temperatures and melting temperatures. So, for instance, PMMA, not a very typical additive manufacturing material, but this did not have a melting temperature associated. But these are three materials that you do see in additive manufacturing: nylon, polycarbonate, polypropylene, and you can see the glass transition temperatures for all of these. Note that some of these, like say rubber, we use all the time at a temperature above this glass transition temperature. So that's kind of a good thing to know too, in terms of what this actually means. This is just a kind of briefly what we mean by a polymer. Any questions about that? People who know polymers about accurate? Close enough. From my understanding of polymers, you don't have conditions of 100%. That's my understanding. So metals would be examples of where you have oftentimes completely crystalline structures, and it has a very well-defined melting temperature. But as far as I understand, those are some really fancy designer polymers that I'm not aware of. Is that they all have an appreciable amount of this amorphous region in them. Okay. Okay. And we're talking about high crystallinity, or we're talking around somewhere around 80–90% crystallinity? Even less than that. Okay. Like for instance, nylon, I'm not sure what the level of crystallinity in that is, but I think it's really, really low. Less than 10%, I don't think. Yeah. All right. So going back to this liquefier, which really isn't liquefying it, it's just bringing it above the glass transition temperature. We have two basic regions. We have one region, which is the liquefier itself. And I'm not going to go into this too much because a variety of reasons. One is that actually defining the PDE that describes melting here is fairly difficult. And it requires computational methods really above what we talked about in this class. And the other thing is that these are designed with feedback controllers such that these wall temperatures hit some sort of desired temperature. Okay? So if, for whatever reason, your environment is colder that morning or that afternoon, where it's exhausting heat more readily, we have feedback controllers to continually regulate. So this temperature of this wall, of this liquefier, is staying at this desired temperature. So we have basically engineered controls to keep this at a constant temperature. Feature that kind of gets rid of the physics or the importance of that process. The main idea here is that this material comes in as a solid, and through the transition goes above the glass transition temperature, now continually decrease in viscosity, so it actually flows. And the material then leaves this nozzle. This is where it gets a little more interesting. So if you look at the literature on material extrusion, you'll see a lot of different models of what these filaments look like, with varying levels of complexity depending on how complex the person wanted to make this. Some of the simpler ones and also fairly representative is to assume that this essentially as a nozzle drags across here, the bottom edge of it flattens this top surface, and this is supported if you ever have seen these parts of cross section. And it creates fairly rectangular cross-section filaments, not round filaments. And so we can start to then define, say, what is the cross-sectional area? Of course, that's width times height. of this filament. Perimeter 2W plus 2H. That would be the perimeter of this. But this is then the type of cross sections that we're talking about with material extrusion processes. Okay. And so once we have some sort of assumed geometry, we can start to go through and try and figure out what is the temperature profile. So if we care about basically for how long this material is above this glass transition temperature, and the length and how fast it cools, then we want to start to understand what is the heat transfer in this process, and therefore we want to understand some things like the Fiat number, right? So the first thing we want to do is we want to understand are we losing a considerable amount of heat in this filament due to convection? Now the difference between this sheet architecture as compared to powder bed fusion is I know there are some material extrusion systems that will have fans inside the region to circulate the air, but the vast majority of them do not. Right? So if we just go kind of baseline, we would say that there is no forced convection within this chamber, and then any convection coming from the surface is from natural convection. So the idea, I'll get to this point on that. The second of what this natural convection is, but basically, well, I'll get to it in a second. I'll hold on. So example 6.1 here is, so consider a filament of ABS plastic. ABS plastic is basically if you've ever printed something with a MakerBot or something and you didn't specify what your materials you wanted to use, the person printing it for you probably used ABS because it's readily available and cheap. Pretty common material. So consider a filament of ABS plastic. We're going to assume that it has a rectangular cross section. And then these are some fairly common sizes for a filament material. And then we're going to say surface temperature of 543 Kelvin. All right, and this is just looking at some standard operating windows. This is above the glass transition temperature for ABS plastic. And say that in the ambient temperature of the air, we're using some sort of heated environment. This would be 70 Celsius in this environment. So determine the Fiat number, assuming natural convection at the surface of the film. I'm trying to understand how. Are we losing an appreciable amount of heat in this to convection via natural convection? All right. So when we're going through forced convection for powder bed fusion, I said that convection is kind of a heat transfer via convection is kind of a notoriously, I don't know what the right word for it would be, like underwhelming science, and that a lot of this is all based off empirical relationships. We're talking about convection. So empirical relationships, and then all those empirical relationships are very much dependent on geometry and scaling factors, etc. And so if you really want to apply this to any type of problem, you have to get into a heat transfer textbook and go through what is your geometry, what type of convection are you working with, all these factors. And so this is the case of going through this for the case of natural convection on a flat plate. So if this plate was at a slight angle, we would use completely different equations based off the relationships people have derived before. Okay, but just so here's the basic problem. I want to quickly talk about natural convection on a flat plate because I think it's a little bit less intuitive than forced convection, which is what we had with powder bed fusion. So natural convection from a hot plate. So we have a plate, and by hot plate, all we mean is that the temperature of the plate is hotter than the temperature of the surrounding fluid. If it's a cold plate, we would just say the opposite. So natural convection from a hot plate, what we have is this hot region. What this does is it basically heats up the gas immediately just above this hot plate, that expands the gas, that makes the gas of lower intensity. So then there's now this buoyancy force driving the gas upward. Right? Simultaneously, you have, as the air moves upward, it cools because it's getting closer to this T infinity temperature. And so then you get these circular patterns in the air above the plane. And that causes convection, which is called a natural convection, because it's not externally driven by, say, a fan or a compressor or whatever you may have for other types of convection heat transfer problems. So the set of equations to derive then what is the natural convection, what is the heat transfer coefficient for natural convection, you have to go to basically a textbook and look at the types of convection and go through and figure out, all right, what is my geometry? What's the orientation of my geometry? And what are kind of the boundary conditions that match some of the empirical relationships that people have derived over the years. So this is just walking through one of those. And so this problem, we're going to be using the Nusselt number again, which is what we saw with forced convection. We have the forced convection. But now, in that case, the Nusselt number was a factor of a different parameter called in that case, it was the Prandtl number and the Reynolds number. Here, we actually use the Rayleigh number. And so the Rayleigh number is a factor, that should be indented. Rayleigh number is a factor that includes basically buoyancy forces, and so therefore you have acceleration of gravity in this Rayleigh number, temperature differences, and some sort of fundamental length, and also viscosity and diffusivity terms. So what this is looking at is basically what is the ratio of forces in this fluid driven by buoyancy forces, some sort of temperature difference in the fluid, compared to viscous forces, also with a factor of now conductivity in that gas itself, is what the Rayleigh number is. Kind of a very brief overview is what it's trying to capture. Does that make sense? Okay. We can also look at normalized, this isn't necessarily a normalized length, it's not a non-dimensional number, but we can look at the cross-section divided by the perimeter as a sort of length variable for the types of structures that we have. Right, so we're going to evaluate this. Right. Questions on that? All right, so this is all getting down to the Via number. Via number, as a reminder, we are trying to calculate ratio of convective heat transfer to conductive heat transfer. This is given by this equation here. And the whole problem here is we're trying to find an effective convective heat transfer problem for this type of natural convection. K, we can get from, that's pretty well established in terms of what is the thermal conductivity of, say, ABS plastic. You can find this information. For this problem, I was looking at this paper, which looks at a lot of modeling of heat transfer in ABS plastic. So this is going to be K, and this is going to be Thomas Rodriguez. Presented at the Solid Freeform Fabrication Symposium conference every year in the year 2000. This is a fairly old paper. And so they reported for ABS plastic a thermal conductivity of 0.177 watts meters inverse. The L in this case, so conduction, occurs in this direction. And so the L in this case is going to be equal to 0.02 Kelvin. So then the difficult part here is finding H bar. Right? H bar. Once we have the Nusselt number, we essentially have this. This is going back to, once you have a Nusselt number, you have this. This is going back to notes from calculating the convective heat transfer coefficient for powder bed fusion. But the main thing is the Nusselt number changes when we talk about natural convection on a flat plate. We're going to use these relationships. So first, we're going to do is to calculate what the Rayleigh number is for this particular problem. So G, acceleration of gravity, right? 9.81 meters per second squared. Beta is 1 over the temperature expressed in Kelvin. And then L is this normalized length, and then we have then viscosity terms and diffusivity for the fluid that we're using. I don't specify specifically the problem, but this is, stagnant air. The far field is stagnant air, that's at this temperature. So we're looking at what is then the viscosity and diffusivity of air. Okay. So these type of properties would be in any heat transfer textbook. So table A4 from a standard heat transfer textbook from Arrow. And we're looking at air at 343 Kelvin. So properties contained with. So with this, we have viscosity. We'll eventually need the conductivity of air. And we need the diffusivity of air. Beta is 1 over the temperature expressed in absolute temperature, so we have to have this in Kelvin. This can be equal to 1 over 343. And then our L bar is the cross-sectional area over the perimeter. So this would be WH over 2W plus 2H. Okay. So this is 6.67 times 10 to the negative 5 meters. Save everything we need to attempt with a Rayleigh number. So Rayleigh number. So again, this should be a non-dimensional number. Yeah, Kelvin's here. Kelvin's cancel. We have units there, seconds to negative 2, right? That's gravity. So we have seconds cancel, and then we have meters to the fourth at the top, meters to the fourth at the top, right? Yes, it gives us a number. Okay, so this gives us a Rayleigh number of 2.7 times 10 to the negative 3. This is a really, really long Rayleigh number. Comparison to a lot of other problems. So I think fortunately this is going to give us very, very little natural surface, but this is a really long number compared to what a lot of problems look at in heat transfer. Nusselt's number from this is equal to 0.54. Rayleigh number is 1/4. Again, did I give myself page? Yeah. So then, this is going back to the notes on convective heat transfer coefficient from the hot diffusion examples. But if we have the Newton number, we have what we need to calculate gas H. Yeah, so we just calculate the Newton number. The value of 55 watts per meter squared per Kelvin. It's actually in the ballpark of what a lot of simulations for the convective heat transfer coefficient is for these different modeling. So I've seen everything from in the 30s to 50s. Okay, so it's about. Then once we have this, we can evaluate the VI number. Okay, so we can start to establish that the VI number is about 0.063. So we're saying is that the convective heat transfer is about 6%, and of course we have to say in relation to something else, right? Convective heat transfer is about 6%. The primary conduction method is a student or primary heat transfer method is a student conduction. But convective has a more of an influence on that powder diffusion. Okay. If you look at this, in the powder diffusion case, we actually have forced convection, which is going to generally be stronger than natural convection. But the biggest difference is that for metals, we had conductivities in the range of 30, and for polymers, we have conductivities in the range of 21. Right? There's about 2 orders of magnitude difference in the conductive heat transfer, the conductivity of the material, right? In terms of changing this balance. Any questions on that idea? Yes. What's the reason? Because I don't have a good answer for you. That's been what's been established in heat transfer textbooks for natural convection. I'm not sure the real rationale for that. With convection, a lot of these are empirical relationships that I have. This one you can solve by hand. They give empirical relationships. So there's not someone over the course of time has established that this is a good scaling factor for balance. Right? And I have a better answer than that. All right, so just with powder bed fusion, we can look at cases where is radiation important, so we can do very similar analysis that we did with powder bed fusion, or we have a considerable amount of radiation from the surface. So again, to remind you, conductive heat transfer. Is this right here. Same conductivity K as before, right, with ABS plastic. So we're going to get then negative 0.177 is inverse, Kelvin inverse. Right. Conduction is in this direction, is just a kind of a first glance of what the appreciable radiant heat transfer here. Right, hot surface on the top, base temperature what we're working on is below here. And so we're going to have a difference in temperature of 543 minus 343. And then L is the direction of the heat transfer, which is going to be 0.2 times 10 to the negative 3 meters. So radiative heat transfer is a reminder. Radiative emissivity, Stefan-Boltzmann constant, and then temperature is raised to the 4th. So if you look at tables for emissivity of plastics, they're quite high. They're almost to 1. So looking at a bunch of different polymers, they're all in the range of about 0.91. So we're going to use approximately 0.9 just to give us a rough estimate of what the emissivity is and the ratio of radiative heat transfer to conductive heat transfer. So emissivity, we'll say, is 0.9. Plastic, which again is much higher than metals, right? So metals are talking about 0.3 range. So radiative heat transfer, 0.9. And then we have Stefan-Boltzmann constant, 5.67 times 10 to the negative 8 watts meters to the negative 2, Kelvin to the negative 4, and our temperatures. now we can look at the ratio of it. Right? So you don't really see conductive heat transfer on the order of 10 to the 5, right? Radiant heat transfer on 10. So we have a good idea of rough order of magnitude here, just to make sure that Q rad over Q conductive, we get 0.02. And so we can safely say that radiation, radiant heat transfer, is not appreciable as compared to conduction. Okay, so if we go back to the powder bed fusion example, we said that convection in that case, or natural convection, or forced convection into the environment. In that case, not talking about the melt pool. Melt pool convection is very high, but convection into the environment, pretty low, less than 1%. And then radiant heat transfer was fairly high. That was in the order of 10%, even though we still chose to ignore it. This is actually the opposite case, where we're saying that there is some natural convection, but the radiative heat transfer is very, very low. And it for the Biot number in terms of convection versus conduction, it had to do with basically the conductivity of polymers being low compared to the conductivity of metals. Here, the radiative heat transfer to conduction ratio is actually mostly to do with the fact that we're not using as hot a temperature when we're talking about polymer melt, right? Or polymers above glass transition temperature, right? So in powder bed fusion, we're using temperatures in the order of 1,000 Kelvin, even higher than that, right? So if you look at the radiative heat transfer, where these temperatures are risen to the 4th power, that's a really strong application of radiative heat transfer. Here we're looking at differences between the baseline temperature, the environmental temperature, and the temperature of the hot force not being all that much. We're somewhere around 200 Kelvin, which is not that much of a difference in comparison to powder bed fusion. So you kind of see a reversal in terms of what effects are. Any questions about that idea? So for the life of me, I cannot find the ratio or the change in surface tension with respect to temperature for polymers. To see if there's any type of Marangoni convection. No one reports it as far as I can tell. People who model material extrusion, they never talk about Marangoni convection. So I think it's pretty safe to say it doesn't really happen. Polymer melts have a considerably higher viscosity to them. Hi. A blueprint? I don't think so. So I don't see anyone report any discussion about Marangoni convection happening in material extrusion. I think it's safe to say it doesn't happen. The viscosity in polymer, basically polymers above the glass transition temperature is considerably higher than viscosity in molten metals. Molten metals flow like water, essentially. They're very, very low viscosity. So I haven't seen any report of this, so I'm going to safely assume that may not be too satisfying, but that's really the reality of the modeling of these types of processes. So on Thursday, I'm not Thursday, today's Thursday. Tuesday next week, we'll get into this very first problem. We won't have time to finish this today, so I just want to start it, and then I'll also give you a little bit of a thought assignment for the weekend as well. So what we're going to look at here is basically we're trying to understand where's the temperature. All right, so once the polymer melts, leaves the nozzle, which is right here, what is the estimate for the temperature along this pipe? Okay, so how does this solidify as we go along this way? This is just giving some really basic temperatures of the filament at the exit of the nozzle. This is essentially, what is that? 270 Celsius, right? And then this would be just elevated environmental temperature, a little bit above room temperature. And we're saying that we're depositing or extruding this into a base at this environmental temperature as well. So we'll get into this on Tuesday's lecture. Just to note, Tuesday we have class. Thursday next week we do not have class because it's fall break. So that's also the kind of the midterm of the term as well. Okay. So a few things since this class is new, and this is there's a lot of uncharted territory for me, and really there's no textbook for this. I think we're far enough into the semester which you can probably comment pretty well on my style, what you like about the class, what you don't like about the class, things of that nature, suggestions for improvement for the second half of the semester in terms of getting something more out of the class. So over the weekend, think about what you think about the class, and on Tuesday I'll just pass on like a piece of paper that has a few questions for you about things that you think I could do to improve, what has been effective for learning in this class, what has been interesting, etc. Just over the weekend, think about that so we have some things that I can try and integrate into the class for the second half to hopefully improve it in case there's something you don't like about the class. So just think about that, and then we'll get it. Then we'll go into fall break. So. Any questions on the material extrusion? Yes, AJ.
Like on the coordination we did,
So there, I'll pull up a paper that goes through this a little bit. I don't have any like slides on this. I think it's worth discussing. So there's two things. So as you saw, well, yes, really quickly, as you heat up a polymer, it expands. That is given by this kind of just generic plot, really quick, right? So this is a specific volume, right? So you heat it up and it expands a considerable amount. So it will definitely expand, like every material except for, well, there's some probably other exceptions, but water would be the notable exception, right? So just like any material, it does expand. And then the other thing that I wasn't intending to talk about, but I think it is a good question. So let's just address that really quickly. If I can find it, there we go. So this is a review article on basically process design and modeling of melt extrusion additive manufacturing. So what we're studying right now. So the one thing also to look at, and there's this nice schematic. I believe it's this paper. There we go. Something called die swell. Yeah. All right. So what you have is you have a right at this tip, and actually throughout the whole area here, it's under pressure. All right. So it's actually being compacted a little bit because of being under in a pressurized environment. Okay. So you have expansion that is happening because it's being heated up. You also have the alternative, which is that under pressure it actually compacts some. As soon as you leave then the nozzle, you have a release of that constraint, and so you actually get the material to swell right at this exit here as well, which is a phenomenon that definitely happens. Is that kind of the question you're asking about, or is that were you talking about thermally driven expansion as well? Okay, so in terms of having residual stresses build up as well.
Yeah, like, if you want to have to be a certain size.
Yeah. Okay. So this would, okay, so maybe I misunderstood. This would be the case of basically the nozzle having kind of a local expansion that happens. When we start getting into discussions of residual stress, we'll talk about as you get to be fairly large parts and you have regions that are hot and regions that are cold, and you try to mix them together, you get residual stresses that form apart, and that can cause breakage in powder bed fusion. It can cause breakage in material extrusion. All these processes, I think additive manufacturing processes are cool. I really like them, but they also do some things that you don't necessarily always see in other more uniform, I guess, manufacturing processes that apply heat in a more uniform fashion. So if you look at, like, for instance, injection molding would be the more traditional competitor to material extrusion. There you're injecting, everything is hot at once, and it's, of course, it's cooling once it hits the cold walls of the die, but everything cools essentially at the same time. Here you have the case where you're heating it very locally in one region where the other area is at the ambient temperature. So you're creating temperature gradients, which can have very negative effects to that. That's a big problem in powder bed fusion too. It's something that I looked at a lot in powder bed fusion actually. We had a 2-year project where we looked at these type of problems. But, yeah, it's a problem with anything additive manufacturing related. And then you have, for powder bed fusion, the solution is sometimes just to raise the ambient temperature everywhere so your gradients aren't so sharp. With material extrusion, you have some issues that if you hold the polymer at an elevated temperature for a long time, it starts to slump, and things that you don't necessarily get in metals. So you can't just like have the base temperature just barely below the last transition temperature and kind of work in that window. You get deformation at temperatures getting close to the last transition temperature too. Any other questions? All right, see you on Thursday. Do you my email?
Yes. Did you send that last night or this morning? Okay, because my inbox has a weird thing where it doesn't give me the correct time a lot of times when the emails come in. So I would. You said tomorrow at 10:30. I wasn't sure if you meant Friday at 10:30 because I got the email today. Okay.
It's almost right now. It's 10:30, right?
Yeah. Yeah. So yeah, right now 10:30.
Okay. Let me unpack and I'll get to my office.
Okay.